Okay, so for this problem, we have a car going around a curve in the road. A curve in the road is a circular path. We're going to figure out the maximum velocity the car can have before it starts to slide out of its circular path by following the 3 steps to a force problem. Step 1, free body diagram. Step 2, sum the forces. Step 3, solve the algebra from the sum of the forces. So the first thing, free body diagram. We need a special free body, not a special free body diagram, but we need to put ourselves in the best location to do our free body diagram. And I'm just going to tell you what it is. We want to do what I call a head-on free body diagram. That's what I'm trying to say. So a head-on free body diagram is as if the car is about, as awful as it sounds, the car is about to run you over, okay? So here's my picture of that. Here's the car. You're looking at the front of it. Here's the headlights right there. Here are the wheels. And there's the driver in the car. So the car's coming straight at you, okay? Now why is that the best place to be? It's the best place to be because you can see all the forces involved in the problem. We got mg down, we've got normal force up, and then let's say the center of the circle is over here. That dot represents the center of the circular path right there. And remember, center of the circle is always positive because that's where the acceleration points. Now, what is the force that keeps the car in the circle? There has to be a force directed to the center that keeps the car in the circular path. It's friction. Now look, I just want to make a comment here. Earlier in the year, when we did friction, friction was opposite motion. You know, so if you look at the side of a car here, so now we're looking at a car from the side. So let's say the car is moving that way. Let's say the motion's to the left. Then friction would be to the right. You know what I'm saying? Look, this friction is not that friction, right? This is a static friction. You know, is there any motion? Is the car moving this way at all? Or is the car coming straight out of the screen in your face? The car's coming straight out of the screen, right? So there is a friction pointing behind the car, but we don't care about that friction. The friction we care about points to the center, okay? Do you guys follow what I'm saying? So there's 2 frictions present. We're focusing on the friction that points to the center. All right, so that's the free body diagram. The next thing we do is we sum the forces x and we sum the forces y. So here's the x direction, there's the y direction. Okay, what's the only force in the x direction? Friction. Sum of the forces equals ma. This A is a centripetal. How do I know it's a centripetal? Well, because the car is in a circular path, and this frictional point, that frictional force points to the center of the circle. So that's a centripetal acceleration, and centripetal acceleration equals v squared over r, which we're going to plug in there. All right, in the y direction, we have normal force up, mg down, sum of the forces equals ma. Is there any acceleration this way? Nope. Is there any circle in that direction? Nope. No acceleration, so we can set this a equal to 0. Okay, so that goes to 0. All right, so the rest of this problem is algebra. Okay, so, oh, and by the way, what's the equation for friction? Friction has an equation. Mu Fn, and this 0.4 right here is the mu. All right, so doing the algebra, I'm going to plug in for friction. So we have mu Fn equals m v squared over r. Now, what's Fn equal to? What's the normal force equal to? mg, so plug that in here. So now we have mu mg equals m v squared over r. The m cancels. You know what? We didn't even need the mass of the car here. The mass of the car doesn't matter. It cancels out. Okay, so doing the algebra, we get V equals square root of mu g r. So you plug in mu, 0.4, gravity's 9.8, the radius is 20. So when you plug the numbers in, you get 8.85 meters per second. Do you guys follow this? So friction points to the center. It's the centripetal force. So it's equal to mv squared over r. Friction is mu times normal force. So you plug that in. So it's a good problem. Any questions on this? Yo. Yeah, I only mentioned that there were two different frictions because kids will remember earlier in the year we talked about friction being opposite motion, which is true. You know, this car, there is a frictional force pointing into the screen, like behind the car. That would be the kinetic friction. But this friction here would be called a static friction. Why would we call that a static friction? Is the car moving this way? Or is it moving out of the screen? Out of the screen. There's no motion in the x direction. So we call that a static friction. The friction pointing behind the car would be a kinetic friction.